We will discuss about vector analysis. Today's topic is coplanar and collinearity. Coplanar vectors and collinearity. Let's see this topic. And before we start, I first tell all of you to subscribe this channel. If you have not subscribed, then subscribe this channel. And if you like this video, then like, share with your friends. And if you have any suggestion, then comment me. So let's start. And first, we know the definition. Definition. What is first? We know what is collinearity. Collinearity means if in a 3D, take a diagram. Then collinearity is defined that if any vector in 3D, this is PQ, uh, this vector PQ, this is a vector I am taking, and its support is PQ. So PQ is support of the A vector. If two vectors also, another vector B vector, have the same support, PQ is the same support, then they are called collinear. And it can be a one case. This is a case one, that both have same support, both have same support, both vectors, vectors A and B have same support, and B have same support. Support means the line, directed line PQ have same support, or case 2 is that case 2, if the two vectors are parallel, if we take another vector C in this way, which have same direction and parallel, then this is I am taking uh, capital AB. So if the vectors, this is C vector, if the two vectors are parallel, if two vectors have parallel support, A and C, have parallel supports, parallel supports, then also they are called collinear. These two cases, if, if anyone is satisfied from one of them, then they are called collinear. Here A and B are collinear for the case A because they have the same support PQ, and here A and C for the case 2 are collinear. This is A vector and C vector support are parallel to each other. So they are collinear. So this is the definition of collinearity. So how can we represent any vector? Like here, B can be represented in this in case with respect to A for the collinearity case. You can take any scalar lambda A vector, or C vector also can be represented by any scalar eta A vector. So also C vector and B vector has relation. So C vector, C vector and B vector also can have a relation. So we can give a relation like kappa A B vector. All are collinear. So that's why they can be written down in this way. If just through a scalar lambda, eta, kappa, all are scalars. Just if they are collinear, then any vector can be represented by another vector by multiplying a scalar. So this is the difference of collinear. Now we study coplanarity. Two vectors are called coplanar if coplan means same plan, either xy plan, x or yz plan or xz plan. So uh, two vectors have two vectors are called coplanar if they can be represented by in this way. Any two vector we are taking like a vector and c vector. We can find out two scalars lambda a vector plus eta c vector. So here, if vector can be represented by two scalars in this way, then they are said coplanar. So in this way, vectors can be represented. Here eta, lambda, and eta are scalars. So now we study some properties of coplanar and collinearity. That first property is that the necessary and sufficient condition, the necessary and sufficient condition condition that three vectors for three distinct points using three sufficient condition for three vectors to be collinear, that they are parallel, they are supposed to be are parallel or on the same line, parallel, collinear, collinear is that there exist three scalars like lambda, eta, and kappa. We can find out three scalars such that not all zero. They are not all zero. They will form linearly dependent. Not all zero. It means that they will form linearly dependent system. Not all zero. Such that lambda a. I am taking three vectors A, B, C. Three vectors. Here I am taking A vector, B vector, and C vector. So they will be collinear. Uh, if this happens, lambda A vector plus eta B vector plus kappa C vector is equal to 0, where the scalars satisfy one more condition, that their sum lambda plus eta plus kappa must be equal to 0. So if we can prove this, if three vectors needs to be collinear, then the necessary and sufficient condition is that the three vectors can be represented in this way, where lambda, kappa, and eta, we can find out any three scalars and their sum is equal to 0. It is very easy to prove. I am proving this. Let's see. So first we prove that this is a necessary. Necessity we will prove necessary. The condition is necessary. So how can we prove? So we take that three vectors A, B, C are collinear. If three vectors are collinear, then the condition is necessary or not. We are trying to justify. A, B, C three vectors are collinear. If three vectors are collinear, then then the vectors I am taking in diagram. I am taking two Cartesian plan. Dimensions are Cartesian plan to understand this. Taking this represent a vector and this is OA, and this represents B vector. This is OB and this represent, if we join this, then this represents C vector. This is C vector. So these are the OA, OC and OB are the position vectors of ABC. So OA, OB in the Cartesian plan, two-dimensional Cartesian plan, they are the they are the position vectors of the these vectors are the respective position vectors. Respective position vectors. Now, what we have to understand that for the necessity that if we take the vector C, the point C divides the line segment AB into M is to N ratio, into M into A ratio. C divides AB into M is to N ratio. Then what is the coordinate of C? Then the coordinate of C, then C vector can be represented. And we know C vector can be represented by in this way M B vector plus N A vector by M plus N. If the division is internally, then this is the formula. Find out the division point of any line segment. Uh, the position vector, the vector division point of the vector or the position vector of the division point. Uh, Division point makes whatever the position vector. The position vector can be represented by this formula if there are two another position vectors. In this way, the position vector OC can be represented by if M is to A is internally divided. Internally AB is internally divided into M is to A by the position vector OC. That it can be represented in this way. Now we can write what? We can write down this in this way. Here you can write down this is NA vector plus MB vector minus M plus N into C vector is equal to 0. If we put N is equal to lambda, N is equal to lambda, M is equal to eta, and minus M plus N is equal to kappa, then we have the required condition that it can be represented in this way. The three vectors lambda A vector plus eta B vector plus kappa C vector is equal to 0. And other condition also can be satisfied in this way. If we sum of these lambda, eta and kappa, we sum lambda plus eta plus kappa, and if we put this value, then it is n plus n minus n minus n equal to 0. So this is necessary. If three vectors are collinear, then they must satisfy these two conditions. And now we will prove the sufficiency of these two conditions. So sufficiency can be proved in this way. Sufficient. These conditions are sufficient to make three vectors collinear. So we have a relation that three vectors are with a relation lambda a vector plus eta b vector plus alpha c vector is represented by in this way equal to 0 where uh, lambda plus eta plus kappa equal to 0. So this is the given condition. We have to prove that this is enough sufficient to make the three vectors collinear. So how we can prove this? From here we will get lambda plus eta lambda plus lambda plus eta is equal to minus kappa. From here we will get that lambda a vector plus eta b vector equal to minus kappa c vector. Now if we divide with lambda plus eta on both sides, then we will get lambda a vector plus eta b vector by lambda eta and here minus kappa c vector. So this is equal to minus kappa. So here will be minus kappa. So we will get c vector. So you can look this any vector any vector can be represented by two vectors line segment uh, two vectors joining a line segment which is divided by lambda is to eta. So here C vector divides the line segment joining A vector and B vector. Actually, you have to compare to Poisson vectors, then you can very easily understand the line joining two vectors A vector and B vector in the lambda is to eta ratio. Lambda is eta ratio internally. So what does it mean? It does mean that three vectors lie on the same line. Three vectors must lie on the same line. It does mean, or the vectors. If you compare the vectors to Poisson vectors, then the point uh, where the vectors represents uh, those points, which points represent these vectors, the point representing C vector in Poisson vector divides internally the line segment of the points showing the position vector of A and B vector internally lambda into eta ratio. So the 3 points lie in the same line. The 3 vectors lie in the same line. It does mean that they are collinear. So these conditions are sufficient to prove that 3 vectors are collinear. So this is our proof. So more topics will be discussed later. So if you like, then like this video and share with your friends. And to continue to get continue such kind of videos, such as this channel. If you subscribe, then you will get earlier the notification of uploaded video. So must subscribe and like and share with your friends.